Hello everybody, this is Mr. Ray with our next lesson in grade 11 University Math. We are working in the Functions and Transformations unit, and we are now at lesson 6. We're talking about transformation still, and as I mentioned in the last lesson, today's lesson is where we actually combine the translations from lesson 4 and the reflections, stretches, and compressions from lesson 5, and we're coming up with multiple transformations and how we sketch those graphs, and where do we get the parameters from? How do we use those values of A, K, D, and C? Okay, so definitions here. Again, transformations in general, those are comprised of translations, which is the left, right, up, down shifts of the graph. Doesn't change the shape of the graph, changes the position. The reflection could be either horizontal reflection or vertical reflection, depending on where whether the A or K parameters are negative, and we'll talk more about that. Stretch and compression, that's your A and K value as well. K is responsible for horizontal stretches and compressions. A is responsible for vertical stretches and compressions. And I got the information about how do you know if it's a stretch or compression based on the value. Okay, so you can review that again. So the key concepts. Stretches, compressions, and reflections. That's basically coming from the A and K parameters. Those can be performed in any order, but they have to be done before the translations. And that's a key point. So when you're applying these transformations, you have to make sure you apply any reflections, stretches, and compressions first, and then you apply the horizontal and vertical translations. And that's related back. You'll see it more next lesson. It's related to bed mass. Stretches, compressions, and reflections are multiplication. It's using the factor, which means you're multiplying, whereas the translations, you're adding and subtracting, and bed mass tells us that multiplication is always a higher priority than adding or subtracting, and that's the key reason why we do the transformations in that order. Translations always last. Okay, now here is the key formula. We've kind of been developing this over the last 2 lessons, but now we're combining the things we learned into one formula, and you can see basically we're starting with f of x, and f of x, we'll refer that as the base function. Could be one of those 5 base functions we talked about earlier in the unit. And you can see g of x as a function of f of x. Here's your f. It's getting kind of hidden now with all the parameters. So we've got the a to the left, so we're multiplying outside to the left. That's going to be your vertical stretch, compression, reflection parameter. That's how you know when you see a number whether it's going to be A or K, based on is it in front of the actual base function to the left of it. At the end, we've got our C value plus C. That's our vertical translation. And inside the bracket, inside basically the function notation for f, we've got the K value, which is multiplying. That's responsible for your horizontal stretches, compressions, and reflections. And we have our D parameter, which is the horizontal translation. So anytime you have an equation and you want to figure out how to graph it, well, we need to pull out the values of A, K, D, and C. And once we have those, and once we have the base function, we're golden, because we can then apply the transformations to the original base function. Okay. So here's just a list. I just talked about this, A, K, D, and C, and what they basically mean. Now the reflection, if you remember from the previous lesson, if A is negative, that means you have a vertical reflection. If K is negative, you have a horizontal reflection. And depending on the absolute value of A, if it's between 0 and 1, it's going to be a vertical compression. If it's bigger than 1, you have a vertical stretch. Now K is the tricky one, remember? So once you get your K value, the actual factor is 1 over K. And if 1 over K is greater than 1, that's going to be a stretch, horizontal stretch. If it's between 0 and 1, it's a horizontal compression. And if K is negative, like I've said before, that's going to be a horizontal reflection. Okay, so these are the key parameters that you're pulling out of your equation, and from these we can describe the transformations as well as use them to create a sketch of the resultant graph of g of x. Okay, so this will be a fairly short lesson compared to the last couple. What we're going to do is 2 examples of transform functions. So in the first example, we've got our base function f of x, which is x squared, quadratic base function. And here is our definition in function notation form of g of x. It's equal to 1/2 times f of 4x minus 3. That's the input for f. And then we subtract 2 in the end. Okay, we're going to do a little sketch over here. So the first thing we're going to do is pull out our values of a, k, c, and d. And you can see here, since that number is to the left of the actual base function, we know that that's our value of a, so a is 1/2. Okay, then we come along here, we can see that that multiplier there, the 4, since that's inside, that's part of the input. That means our k value is 4. The next number we encounter is the 3 or the -3. And remember, we relate this back to x minus d, so that tells us d is 3. That's going to be our horizontal translation. And finally, on the far right, outside the function notation, that's going to be our c value, which is our vertical translation. Okay, so now that we've got our 4 parameters, we can get going on what the question's asking. So let's maybe read the question, which would have been good to start off with. Describe the combination of transformations that must be applied to the base function f of x to obtain the transform function. Then write the corresponding equation and sketch its graph. Okay, so based on these values, and you know we have to, as we mentioned earlier in the lesson, we have to talk about the A transformation and the K first before we talk about D and C. So in terms of the transformations, I'll just list them here. So the first thing that happens, and it doesn't necessarily have to be in this exact order, as long as A and K is listed before D and C. So the A being 1/2, okay, that tells us, well, first of all, it tells us there's no reflection because it's not negative. The value of 1/2 tells us it's a vertical compression, and it's by a factor of 1/2. So vertical compression by a factor of 1/2. Okay, and then so that A is taken care of. We didn't have to mention any reflection because there is none. Then we move along to the K. So remember K, we have to do the 1 over K to get the factor. So the factor of this horizontal stretch or compression is 1/4. And the fact that the factor is between 0 and 1, since it's 1/4, tells us also that this K value of 4 means it's a horizontal compression by a factor of 1/4. So that's going to come next. And I could have listed in either order. I usually start with A because it's left to right, but it could be flipped in the order there. So now we've talked about A and K. Now we can finally move to D and C because we've taken care of the stretches, compressions, and reflections. Now we can talk about the translations, and I'll combine these two together just to save, make our list a little bit shorter. So translated, so the D value being 3 tells us horizontal 3 means, positive 3 means to the right, so 3 units to the right. And then the C value of 2 means that's translated 2 units up. So I'll just tack that on to the end of this one, and 2 units up. Again, it doesn't matter whether you talk about the horizontal or vertical translation first. You can do either one. Okay, so that's basically, there's our list of a description of the transformations that would be needed to go from f of x, the x squared graph, to this new transform graph. Okay. So what we want to do, because it says write the corresponding equation. Well, what we've got here is an equation of g of x, but it relies on us to know what the original base function is, because it's reflying. Sorry, it's regarding the function f, which we have to go back to this description to know what it is. So what we're actually going to do is rewrite g of x with the squaring in there, so that we don't have to, know what f of x is outside. This would be the way you'd write the equation anyways. So if I go left to right here, okay, I'm going to write the 1/2, and then I've got my function notation f of 4x minus 3 in brackets. So that's where the function comes in. So this whole, that whole thing in the square brackets, that's the new input. That's what's being squared, okay? So 4 bracket x minus 3 is replacing the x in the original equation. So I'll put that sort of in my double brackets here. And that whole thing is being squared. That's my new input because it's in the square brackets for f. So that's being squared, and then after that's done, we subtract 2. Now, if f of x had been like square root function, well, instead of squaring this whole input, we'd put a square root around it. Or if it was absolute value, we just put absolute value signs around. So basically, it's pretty easy to change back and forth, or at least it should be after you've done a couple of these. The tougher one would be the 1 over x. So the way 1 over x would be 1 over this whole thing. Okay. So we still have a little bit of work to do to simplify this, to make it look more like a regular type of equation. Okay. So the first thing I notice here inside the brackets, I've got 4 bracket x minus 3, the whole thing squared. Now what that means is each of these things, the 4 and the x minus 3, are all being squared. So I'm gonna do both. So I'm gonna put my 1/2 that was there before. Now I'm gonna square the 4, and that's a 16. So I'll multiply by 16, and I could decide to expand that, but I'm going to leave it as x minus 3 squared because I have a feeling this is going to kind of turn into vertex form, if you remember what that looks like. So let's just proceed with this and see where it takes us. So basically I've applied the squaring to both of these, and now I'm going to combine the 1/2 with the 16. So 1/2 of 16 is 8, so that's out front. Then I have x minus 3 squared minus 2, and that's the full equation of the transform function. So I could just decide to graph that based on tools that I know from grade 10. But we're going to do it a little bit differently. So I'm going to start over here. So there's my XY grid. I'm going to start with the graph of x squared. So if I remember my base points, 0, 0 is the vertex. I have these 1, 1 and negative 1, 1. And then I have 2, 4 and negative 2, 4. Okay, so this is my f of x function right here. Try to make it as smooth as possible. Okay, and I'm going to label that just at the top here. Okay, so I'm going to kind of apply these transformations based on what these descriptions are telling me. So I've got there's my base function, and now we do this. We do this set of instructions to come up with our graph. Okay, so the first thing we do is a vertical compression by a factor of 1/2. So what that means is I'm taking all these base points and I'm halving the y values because it's a vertical compression. So that tells me that these 2 points here, which have y values of 4, will now have same x value, but same x coordinate, but a y coordinate that's now 2. And then the points here that had a y coordinate of 1, well, those are halved. So those are now x equals 1 and y equals 1/2, and x equals negative 1, y equals 1/2. So now I've got those 4 new points. The 0, 0, when I half that, it's still 0. So I'm just going to come up with my new graph here. It's kind of to the outside, so it's a little bit, well, it's compressed. It's like I'm pushing down on these arrows. It's a little wider than the original f of x. So this is basically, I'll put a symbol here for this is 1. So I'm applying that transformation. Now I'm going to apply this transformation, which is a horizontal compression by a factor of 1/4. So what happens here is now I'm working with, be nice to have this in color, but I'm now working with these outside points here that I've compressed vertically. And now what I'm doing with those is I'm horizontally compressing it by a factor of 1/4. So that means I'm taking the x values and multiplying them by 1/4. Okay, so again, the 0, 0 doesn't change because 0 times 1/4 is still 0. But this point here, right now it has a x coordinate of 2, so 1/4 of 2 would be 1/2. So now that new point is basically shifted from here to here, and I've got the same thing on the other side at so that value of 2 now becomes 1/2. Okay, and then I take these 2 points here. These x coordinates are 1 and negative 1. So this is getting a little bit ridiculous in terms of tightness. So that turns into 1/4 and negative 1/4. So here's my 4 new transform points, and the 0, 0 that didn't really change. So that is my new. This is after transformation number 2. Okay, so now we just have to do the translation. So we're basically taking this shape. So I'll make this one a little bit darker just so we can see our. Sorry, that's not the right. Is that the right one? Sorry, that's not the right one. The 2 is the one that's the closest one here. So let's put it here. So this really skinny looking parabola is our most recent one, and now we have to actually translate it. So what we do for those 5 base points is we move it 3 to the right and 2 up. Was it 2 up? Oh, I've had this wrong. Sorry. Not wearing my glasses this evening, so that's a -2 there. So we should be okay. I had it -2 here, but that's going to change this description to 2 units down. Okay, so that's better. Sorry for that. So it didn't affect these graphs so far because we didn't apply that transformation, the translation. So for example, that point 0, 0, which is on all of these graphs, I'm going to move that 3 to the right and 2 down. So it goes 3 to the right and 2 down. So that's where my new vertex is. Okay. And then I also do the same thing with these other points. So if you remember, these points were they were 1 up and 1/4 away from the x-axis. So I'm basically just I could do the same thing, 3 to the right, 2 down for all of these. I'm just trying to be a little bit more accurate here. And then the last points on here were at 2 and 1/2. So that goes 1, 2, and then let's make sure I get this right. So that's the point. No, that was 1/2 and 2. I had them the other way around. So this is up here and here. So again, this is a very skinny looking. It should look identical to that shape if I do everything right, but this is a pretty crude looking sketch. So this is the final version of my sketch. So this is after applying the third instruction for the transformation, the 2 translations. So this would be your final graph here. Okay. Now I'll talk about how time consuming and inaccurate this appears to be, and you're right, it is. And we're going to talk about how could we do this in a more efficient manner. And so let's save that for after we do this one. So this second and final transformation, we can see f of x, the original function, base function is square root of x, and this time our transform function is -2 times f of 3x minus 15 in brackets plus 4. Okay, now if you just remember for a second, if we go back to the initial notes, so when I put this box around, this is really important that you remember what this looks like. So what I want you to key in on is what's in the input. So f of what? So it's always f of k bracket x minus d. Okay, so if I look at this, this may look like it's okay, but on the version that I want to use, the k has to be factored out. In other words, I need to be able to see brackets around the x and the d value. In this case, that hasn't been factored out. So if I was to maybe say, well, that looks like the d value is if the d value is 15, I would actually be wrong. And I'm wrong because this version of g of x is not quite correct. Excuse me. Okay. So what I was saying was this version of the transform function is not quite correct. So what we have to do is update it. So the only thing we have to change is this part here because it's not k bracket x minus d. So this part here after the f would be 3 bracket. Okay, so we're actually factoring the 3 out of both of these terms here. So when I factor a 3 out, I get x minus 5. And I've got a second set of brackets now that I've got once I've factored out the 3. So you can see now when I look at this, the d value is actually 5, not 15. And this is the correct version of this. So This is something anytime you see a transform function written in terms of the other function, the base function, make sure that you're actually getting the correct d value. In other words, if there is a k value, was it factored out of both the x term and the constant term inside the input? Okay, so now this has been corrected. This we can actually pull out the values of a, k, d, and c, and we'll do that now. So I can now say that a is equal to -2. I can say that k is equal to 3. And now I can safely say that the d value is 5 and the c value is +4. Okay, and those are the values I'm going to work with when I, first of all, when I list my transformation steps, and also it'll be helpful when I put the values in here to create the new function. Okay, so in terms of the transformation, so again, we're going to start with a and k. I'll start with a just because it's in order from left to right. And the first thing I notice is that a is negative. So my first transformation step will be a vertical reflection. And that takes care of the negative sign in a. But now I have to process, well, what does the a value of 2 mean? And since 2 is bigger than 1, that tells me there's a vertical stretch by a factor of 2. Okay, so that covers all the a parameter, what it's doing in regards to the transformation. Now we look at the k value. The k value is 3. So remember, I have to do the reciprocal of this. 1 over k is the factor. So it's a factor of 1 over 3 for the, in this case, k is going to be a horizontal stretch or compression. And since the factor is 1/3, that tells me, since it's between 0 and 1, that it's an actual compression. So the third step will be a horizontal compression by a factor of 1/3. Okay, and then so that takes care of k, and now we can safely move on to do d and c, the translations. We've got everything in order now. So the last one I'll combine. So d equal 5 means that's a horizontal translation. So I could say translation 5 units to the right and 4 units up. So translation 5 units up and, sorry, not up, to the right. 5 units right and 4 units up. Okay, so that's in order. This, if I took the base graph of square root of x and started applying these transformations, I would get the new graph of this function. And speaking of that function, now it's time for us to write the version that doesn't have the f of x inside of it. Let's change the function f to what function f it really is, and that's the square root of x. So our new version of g of x, this one probably won't be as hard. Okay, so again, I'm reading left to right, so I start off -2, and now everything inside these brackets here, the 3x minus 15, that's the input. That's what's under, that's what we're square rooting. So it's, here's where I'd write my square root symbol, and everything under there is put under the square root. So we take the square root of that, multiply it by -2, and then we do the last part here, we add 4. And you might say, why didn't we factor out the 3 here? Well, you could, but it's just going to make it a little more complicated looking. The reason why we factored it out here was so we get the correct value of D, but when it's written here, we don't necessarily have to have the D, but I'll write it here anyways, just so you can see both versions. So here I'll factor out the 3 so you can see the D value very apparently. So those are the 2 versions of the transform function g of x. Okay, so what we'll do now is start looking at the transformations that we do. So f of x, that's going to be the first graph we do. So if you remember, that is the graph that has an endpoint at 0, 0. Then we have a point at 1, 1, point at 4, 2, and a point at 9, 3. So here's our graph of f of x. Okay, and now let's start applying these transformations we've written down here. First thing we do is a vertical reflection. So what that does is it takes each of these points and kind of reflects this point across the x-axis. So we'll start here. 0, 0 is on the x-axis, so it doesn't go anywhere. There's really no impact on a reflection. But this point, the y value changes from 1 to -1. This point changes from 4, 2 to 4, -2. And this point changes from 9, 3 to 9, -3. So now we've got our new sketch of f of x vertically reflected. So I'm going to put a 1 there just to show that that's... Now this isn't the same graph. These are separate graphs. So the top branch, that's f of x. The bottom branch is basically negative f of x. We were reflecting it. Okay, then we apply a vertical stretch by a factor of 2. So what that says is we take our most recent points after the last transformation, and we multiply all the y values by 2. So again, 0, 0 doesn't change, but this goes from -1 to -2. This one goes from -2 to -4, and this one goes from -3 to -6. Okay, so you can see what's happened as we do our vertical stretch. So that's our second transformation we do. So we've drawn our base graph and we did our vertical reflection and vertical stretch. Now we're going to do a horizontal compression by a factor of 1/3. So what that means is I take each of these most recent points and I basically find the x value and I multiply the x value by 1/3 or divide it by 3, same thing. So 0, 0 again doesn't change, but this point here, the x coordinate is 1. We take 1/3 of that, so that new x value is now at 1/3 -2. This point here is at 4, so if we take 1/3 of 4, that's 4/3, which is 1 1/3, so that's about here. And then we take this point, it's originally 9. 1/3 of 9 is 3, so this goes all the way down to here. Sorry, 1, 2, 3. Okay, so our latest graph now looks like this. So it's kind of guessing at this point, but we'll say that's it there. So that's our third transformation. And now the last thing we do is apply the translation, which tells us 5 units right and 4 units up. So that point at 0, 0, which is our end point at just about every one of these, but we're looking at this line, this curve right now. So that point 0, 0 goes 5 to the right, and then 4 up. So all of a sudden our graph is now shifting from there to there. This point here, if we remember what this point is, this is 1/3 -2. So we go 5 to the right, so that's 4 2/3, and then 4 up. So that goes all the way up to 2. So I believe it's about here. No, it's a little bit over here. Yeah. So there's our first point, there's our second point. Now we do our third point, which is here. So that's that was 1 1/3 and -4. So 1 1/3 plus 5, that would be 6 1/3. And then we go up 4, so that's right on the x-axis. Okay, and then the final point was this one here. This was at 3 -6, so this one's a little easier to work with. So we go 5 to the right, that's all the way over to 8, and then we go 4 up, so that goes up to -2, up to here. So there's our final point. So it's getting a little busy around here, I totally understand that, but we started here and we worked our way down here. So this graph and this graph should look really similar. I know these are not quite exactly the same, but you have your endpoint here, and at this end it keeps going. So this is our final version. This is our g of x, or after the fourth transformation. Okay, so let's talk about what we just did. So I think we can all agree that sketching using this technique is not only cumbersome, it's not all that accurate. You can see I was kind of hemming and hawing about where the points go, and you can see by the actual sketch that it's not entirely accurate. So what we're going to do is the next lesson, I'm going to show you a technique where all you do is one set of points. It's called base point transformations. So we're still using the base points that we started with, but we're not drawing every single transformation as we go. Okay. Now the part that we did here, where we dissected the transform function, we pulled out the A, K, D, and C values, and then we described what's going on in terms of transformations. That is really that's really important. You're going to have to do that still. So we're not really throwing away this whole technique. We're just going to adapt it to become more efficient, okay, and more accurate. So the part that we did here, all the work we did on this side, this is still very valuable and required. What we're going to change in the next lesson is how we go about applying these A, K, D, and C values and the base function to create only the final version, which is your g of x graph. Okay, so that's what we're going to do. So I've got a handout for you to work on, as well as some textbook work to basically combine everything we did in the last two lessons, translations, stretches, reflections, and reflections. So it's really important that you can do this algebraic work, understand what A, K, D, and C mean, be able to create the two different versions of the transform function, the one with the f of x in and the one with the actual thing that f of x does, in this case squaring, in this case the square root. So give these a try. Make sure you're very confident and comfortable with those parameters and how you use them. And then tomorrow's lesson should be pretty gratifying. You'll be able to very quickly graph any one of these functions in a matter of, say, 2 minutes tops. Okay, so that's it for today. We'll see you tomorrow when we look at base point transformation, graphing of functions. Have a great day.